Here we go, Chapter 5, Section 2. This is ionic bonding and salts. Here's the document that you want to have open, the guided notes document. You want to have that open so you can fill in the blanks as we go along. I'm going to project the PowerPoint for you, or the slideshow, and then you guys can fill in the blanks, okay? You'll notice I tried to make this even easier for you guys to fill in the blanks than before because, well, you'll see. So here's your objectives. You see those at the top. And so we have ionic bonding. So pyrite is a mineral. This is an example of an ionic compound, right? But it's made of iron ions and sulfur ions. Okay, because opposite charges attract, cations, and anions attract one another and ionic bond is formed. You'll notice that opposite is highlighted and bolded and yellow. So that might be an important word for you. So I wanted to show you what that looks like on the particle level. So this is what pyrite looks like, right? If you were able to look at the individual atoms in pyrite. So you have your iron atoms here, and you have your sulfur ions here. So you have sulfur comes in 2 ions for every one of the iron ions, because your iron is +2 and your sulfur here is -1, right? And so for everything to balance out, you have it looks like that. So you have ionic bonds formed between ions of opposite charges. So when sodium and chlorine react, you get a stable sodium ion and a chloride ion. Now the sodium ion is called a cation because it is positively charged, and the chloride ion is called an anion because it is negatively charged. You'll notice that we kind of don't pronounce the words properly, like normal English. This is a cation, and this is an anion because, well, because chemistry. And so the force of attraction is attractive because you have -1 charges of the anion and the +1 charges of the cation, and they come together to form the ionic bond. Okay, so sodium chloride is called a salt. A salt is the name given to an ionic compound. So you are probably familiar with sodium chloride. It's called table salt. And so this may be the salt that you think of when you think of salt, but there's literally billions of salts. And so here's a good video of a chemistry professor forming sodium chloride, and you'll see him performing the demonstration while narrated by a non-chemist. I can tell you that it's a non-chemist because he incorrectly describes the orange color as being the sodium flame color. It's clearly the yellow. Yeah, the sodium chloride's or sodium's flame emission is yellow, but I'll let you should watch it. It's awesome. So salts are made of cations and anions held together by those ionic bonds, by those forces of attraction, because they're oppositely charged. However, you don't have a single cation and a single anion. You have a bunch of cations and a bunch of anions. When you get a bunch of them together, they form a tightly packed crystal structure. And so that involves the transfer of energy, okay? And so if you step out the process of making an ionic compound, you will see that there's a lot of steps to it. And each step involves an amount of energy. So you have ionization energy. So that's the amount of energy required to remove an electron. So that would be this energy here for removing an electron from the sodium atom. And then you get a sodium cation and an electron by itself. And that electron goes and flies away and seems like, look, that electron will bond to the chloride, and you get the chloride anion plus energy. That energy that you get from this one is called the electron affinity. That's the energy change when an electron finds an atom. Okay, but that's not on your worksheet. Ionization energy is, though. And then this process continues. Removing electrons is part of the process, but the rest of the process forming salt supplies the energy to make up the difference so that the overall process releases energy. That's very important. So when you form an ionic bond, that whole process releases energy. And That energy we call the ionization energy. I'm sorry, the crystal lattice energy. But we'll get to that later. The process of forming a sodium chloride compound is broken down into a bunch of different steps. Okay, so these steps are listed on your notes. It's not that you need to know these steps, but this is like if you were thinking of this happening on a particle by particle basis, this is what would have to happen. Okay, and so then this is that process illustrated. So you have your sodium and your chlorine, and then you take your sodium and your chlorine, you take it from a solid, you put it, make it into a gas. You take the sodium and you take away its electron. You take the chlorine that comes in a diatomic element and you separate it by itself. And then you get energy back from when you add that electron to the chlorine and get chloride. And then you add energy back when you form this lattice, right? When the positive and negative charges come together, it releases a lot of energy. And that is called the lattice energy. So this is the key to ionic bonding is the lattice energy. This lattice energy gives the ionic substance certain properties. And so you should watch this because this is an illustration of what it looks like when an ionic compound is formed on the particle level. So this really gives you a nice little particle level view of the process of forming a salt. Um, oh, sorry, you didn't really need this part in there, but oh well. So here's the important part about this. Ionic compounds are a ratio of cations to anions. So you have cations and you have anions, and they're held together by the attractive force of opposite charge. Right? When you have molecules, like for example, water. Water is a molecule because you have hydrogen atoms bonding to an oxygen atom. They're sharing electrons, forming a chemical bond. There are no chemical bonds in a sodium chloride. Okay, sodium chloride or any salt is not bound together by bonds, it's held together by that lattice energy. And so it forms a crystal structure, and there are no specific NaCl molecules. NaCl is just the ratio of sodiums to chlorides in the ionic compound. And this lattice energy is what gives ionic compounds super high melting and boiling points. Okay, you find all ionic compounds as solids at room temperature, right? And it takes a generous amount of energy to melt them and even more insane amount of energy to boil them, right? If you've ever tried to melt salt, it doesn't happen. You can't do it on the stove. It's really, really, really hard to do. You have to have a super high temperature crucible, and you do that under a super strong heat source. Um, and I would not recommend doing it because it is terribly dangerous, mostly because it's super hot. Okay, so here's some other salts, right? You have sodium chloride, the table salt, right? But you also have magnesium fluoride, which is different salt, right? Calcium iodide, different salt. Um, and then you have things that are not salts. These are covalent compounds, even though they have like some nonmetals in them, right? The chlorides, the same as before, the fluorides, the same as before. Because they're bonded to nonmetals, these guys are covalent compounds instead of ionic compounds. We're going to talk about them later. But right now, you should notice that the melting point for these guys, notice that's really high, right? Melting point for sodium chloride, 801 degrees Celsius. That is insane. 700 degrees higher than the temperature of boiling water, right? And then you get down to these guys, and their melting point is super low, right? And their boiling point is super low, right? Because they're gases, right? And they're form molecules as opposed to the crystal lattice of an ionic compound. So, in order to conduct electricity, there's two things that have to happen. This is very important for life. Okay, a substance must contain charged particles, and those particles must be free to move. Okay, that's the rules for being able to conduct electric current, right? You have to have charged particles, and those particles need to be free to move so that they can conduct the electricity, right? Because electricity is moving electrons. So ionic solids are not conductors because the ions can't move. So if you have a salt crystal, right? Even though it's made up of charged particles, it won't conduct electricity because the particles are not free to move. Okay, so if you melted it, but then they can move around and they're really good conductors, right? Um, but that's not usually what we do. Usually what you do is you take your sodium chloride and you dissolve it in water. And when you make salt water, now it can conduct electricity, right? Because you take your positive sodium ions, your negative chloride ions, and you surround them with water molecules. And now those particles are able to move and they carry a charge, right? Now, some of the other components of ionic compounds is that they are hard and brittle. What it means to be hard for a substance is that the crystal is able to resist a large force applied to it, meaning that you can kind of hammer at it, right? And it will resist that force. Brittle means that when the applied force becomes too strong to resist, the crystal develops a widespread fracture rather than a small dent. So if you think about if you've hammered metal before, right? Hammering metal is not brittle, right? Metal is malleable, meaning that you are able to hammer it. Ionic compounds are not um, malleable, they are brittle. So if you've ever had like in the wintertime, maybe you've got some rock salt in your garage and maybe it got a little moisture in there and it's like all clumped together. Well, you break it apart by hitting it with a large force, right? And then it shatters into smaller little crystal pieces, right? That's what brittle means. So, um, all salt crystals, all crystal lattices, all ionic compounds are made up of repeating units. Those repeating units are the positive cations surrounded by negative anions, or the negative anions surrounded by positive cations. Those repeating units are arranged in the salt to form a crystal lattice, and that's the regular pattern. So the cool part about salt crystals is that they form crystals, right? And crystals are cool because they're neat shapes, right? And the reason why they have those neat, distinct shapes is because they are made of repeating units of those ions. And so that's the end of the guided notes, right? So crystal lattice was the last answer on your guided notes sheet. But if you want to, you can keep going on in this PowerPoint or in this slideshow, and there's a couple of questions to review sections 1 and 2. So slides 1 through 23 are the ones that have the stuff about the guided notes. The rest of it from 24 to 35 are these review style questions. So feel free to do them if you want to. I'm not going to go over them. They give you the right answers in the PowerPoint or in the slideshow, and you have to like view it as a slideshow in order to do that. But hopefully it'll help to strengthen your understanding. Okay. Don't forget to submit this when you are done. Have a great day, guys.